Before we can get started talking about proofs, we need to go over one subtle difference that we've kind of just brushed over in this class, and that's the difference between congruent and equals. The difference between congruent and equals has to do with what we're comparing. If we're comparing geometric figures like line segments, angles, triangles, we use congruent. If we're comparing numbers, we're going to use an equal sign. Let's look at two angles. Let's call this angle A, B, C, and this angle D, E, F. If those two angles are the same, the angles are congruent. The geometric figure of the angles are congruent to each other. To mark two angles congruent, I'm going to use this arc. If I were to write that out, I would say the angle ABC is congruent to angle DEF. Now I can measure angles. So if I go in and measure angle ABC and find out that it's 36 degrees, and I measure angle DEF and find out it's 36 degrees, those two angles have equal measures. The angles themselves are congruent. It's their measures that are equal. 36 degrees equals 36 degrees. If I were to write that out, I would say the measure of angle ABC equals the measure of angle DEF. Notice when I'm talking about the angles are congruent. It's their measures, their degrees, that are equal. Switching from a congruent sign to an equal sign is the definition of congruence. And much like an if and only if statement, definitions can work both ways. I can start with two shapes, two figures being congruent, and conclude that their measures are equal, or I can go the other way around. If two shapes have equal measures, then those two shapes are congruent. I can use this definition either way in a proof. Let's look at a proof. A proof is stringing together statements in a logical order, each with a reason. For reasons, we can use theorems, postulates, we can use definitions. If we look, our first given, M is the midpoint of segment AB. Okay, the reason I know M is the midpoint of segment AB, that information is given to me. That's my reason for statement number one. Now I'm trying to prove that 2 times the measure of segment AM is going to equal the measure of segment AB. Well, I know that's true. Let's write a logical proof for that. So how can I string these statements together logically to write my proof? First statement is given. Second statement. Well, if M is the midpoint, then these two segments have to be congruent. How do I know that those two segments are congruent? Well, M is the midpoint. That's really the definition of midpoint. The reason I know that these two segments are congruent is because M is the midpoint. That's what this statement tells me. Well, if those two segments are congruent, their measures have to be equal. They both have to be the same length. To switch from two segments being congruent to their measures being equal is the definition of congruence. Notice that each time I make or go from one statement to the next, the reason goes to the right. So I go from here to here, reason goes here. From here to here, reason goes here. The next step is a little bit tricky. the measure of AM plus the measure of MB equals the measure of AB. If I look at my picture, AM plus MB equals AB. Smaller segment plus smaller segment equals my bigger segment. The reason that I can add these segments together and get this bigger segment is the segment addition postulate. Looking at my next statement, I have another segment plus another segment equaling a bigger segment. So it looks like I should use the segment addition postulate again. But if I look at my picture, if I take AM and I add AM, I don't get AB in my picture. In order to use segment addition, these two together have to make up this segment. This isn't true for statement number 5. AM and AM don't equal AB. So how do I go from statement 4 to statement 5? Well, I find out what's changed. AM is the same, the plus is the same, the equals is the same, AB is the same. The one thing that has changed is the measure of MB has turned into the measure of AM. Well, can I make that change? Well, if I look back at statement number 3, statement number 3 told me that the measure of AM equals the measure of MB. Any time that I see the measure of MB, I can replace it with AM. When I make a statement in a proof, I can use that statement later in any other statement to make a new statement. If you look, I've taken statement 3, substituted into statement 4 to create statement 5. The reason that I can make that move? Substitution. And I'm going to put 3 into 4. I'm taking statement 3, plugging it into statement 4 to create statement 5. Last statement. My equals has stayed the same. The measure of AB stays the measure of AB. What's changed is the measure of AM plus the measure of AM has turned into 2 measures of AM. Well, what am I really doing here? Well, if I have a measure of AM and I add another measure of AM, for a grand total I have 2 measures of AM. Similar to algebra class, if I had x plus x, I would get 2x. Really, the measure of AM and the measure of AM are like terms. Since they're both like terms, I can combine those like terms. The reason I can add AM to AM, they're both measures of AM. I can tally how many I have. I have a grand total of 2. Your book will call this the distributive property. Why does your book call this the distributive property? Well, if we have x plus x, that's really 1x plus 1x. And since both of these have x's in them, I can factor out an x. So I'm going to factor an x out of here, and I'm left with 1. And I'm going to factor an x out of here, and I'm left with 1. And I'm going to put that x, I can put that x either in front of the parentheses or behind. I'm going to put it behind. Well, now I can take 1 plus 1 and get 2. So this is really 2x. Your book will call this move the distributive property. I like to just call it combining like terms. Both are acceptable. I like this answer.